Module 3 Mastery Assignment by Leslie Oy. Topic 1. Optimization. Optimization is the process of finding an absolute maximum or minimum value of a function given a set of constraints. When we do optimization, we need to note the first derivative test. The first derivative test is the use of critical values of a function to determine whether a local minima or maxima value exists. Now let's look at the steps of optimization. The first step is to determine what you're trying to optimize. Then, you are to write an equation to be optimized. Make sure there's only one independent variable in that equation. After that, you perform the first derivative test for relative extremia. To do the first derivative test, you must differentiate the main equation and then set it equal to 0, and then solve. Then, you confirm with the number line analysis. After that, you are to compare your local extrema to endpoints of domain. This ensures you have found absolute extrema. And then you conclude and include units in your conclusion. Let's look at an example. Find the maximum volume of an open box with a square base that is to be made from 108 square inches of material. I have highlighted the important terms we need to know to solve this problem. First, we need to determine what we're trying to optimize. In this case, we're trying to find the maximum volume of an open box. So the equation would be volume equals length times width times height. At this point, I suggest we make a sketch. A sketch will help us figure out the formula we are trying to optimize. Now that we have a sketch, we can write a formula for the quantity to be optimized, which will be volume equals x squared times z. However, don't forget, it can only have one independent variable. So now we need to rewrite the formula with one variable. So we're going to use the area formula, which is x squared plus 4xz, to solve for one variable. In this case, we're going to solve for z. So when we do that, we're going to get z equals 108 minus x squared all over 4x. Then we can substitute this back into our main equation. So now the equation to be optimized is volume equals x squared times 108 minus x squared all over 4x. And this can all simplify into 27x minus 1/4 x cubed. Next, we are to determine the domain for the single variable. In this case, x will be greater than 0. This is because if one of the sides was equal to 0, then there would be no volume. Now, we take the first derivative of the equation to be optimized. In this case, v prime is going to be equal to 27 minus 3/4 x squared. Now we can find the critical numbers by setting v prime equal to 0. When we do this, x equals 6 is the only critical number we can have, because it's the only one that will fit in our domain. Now we can perform the number line analysis to verify our relative extrema. When we do this, any values plugged into our first derivative are going to be positive when they're less than 6. However, they're going to be negative if you plug any value greater than 6. Because of this, 6 is a local maximum since v prime changes from positive to negative. Now we compare our relative extrema to our endpoints. In this case, there are none, because if a box side is 0, then there would be no volume, so just stick to the local maximum. Now we plug the local maximum into the optimization equation, which is volume equals 27x minus 1/4 x cubed. V of 6 equals 27 times 6 minus 1/4 times 6 cubed. When we simplify this, we're going to get the volume to be equal to 108. So now we conclude, and don't forget to include units. The maximum volume of the box is 108 cubic inches. Topic 2. L'Hopital's rule. We can't always evaluate a limit with algebra, so L'Hopital's rule is a theorem we can use in calculus to find the limits of certain functions through the use of derivatives if certain conditions are met. We're going to be looking at the limit as x approaches a of f of x over g of x. Suppose f of x and g of x are differentiable, and g prime of x does not equal 0 near x equals a. Then suppose if the limit as x approaches a of f of x equals 0, and the limit as x approaches a of g of x equals 0, or the limit as x approaches a of f of x equals positive or negative infinity, and the limit as x approaches a of g of x equals positive or negative infinity, then the limit as x approaches a of f of x over g of x equals the limit as x approaches a of the first derivative of f of x over the first derivative of g of x. As long as it's one of these two situations, then this theorem works. However, it is important to note that L'Hopital's rule only works for indeterminate forms. Examples of these would be 0 over 0 and infinity over infinity. The limits of indeterminate forms may or may not exist. Now that we know what L'Hopital's rule is, let's apply it to an example. We're going to evaluate the limit as x approaches infinity of the natural log of x all over the cube root of x. When we try to do direct substitution here, notice we're going to get infinity over infinity, which is an indeterminate form. So now we can use L'Hopital's rule. So we're going to take the derivative of both the top and the bottom. And when we do this, we're going to get the limit as x approaches infinity of 1 over x over 1/3 x to the negative 2/3 power. This can be rewritten as the limit as x approaches infinity of 1 over x times 3x to the 2/3 power. When we simplify this, we're going to get the limit as x approaches infinity of 3 over x to the 1/3 power. Now we can no longer apply L'Hopital's rule to this problem because it is no longer in an indeterminate form. So, 3 over infinity is basically going to be equal to 0. This can be verified through graphing.